All right, so we're pressing forward, and hopefully today we finish chapter 2, and then we'll get into chapter 3 next time. This is a derivation of the heat diffusion equation. Start with a small control volume or control volume anywhere, it's arbitrary, in your material. So don't think that this encompasses the material. Think of the material as extending well beyond, and you just pick a control volume inside the material. Then you perform an energy balance for that control volume, and you say, can the energy that I'm keeping track of, which is only internal energy, can it accumulate in that control volume? Yes. So we're going to, in our energy balance, we're going to talk about accumulation, as well as can it be conducted across the boundary of that control volume? Yes. One side could be hot, one side could be cold. So you could have conduction across the boundary. So we need to keep track of that in our energy balance statement. And then, could we have some magical generation of heat? Where would that come from? Chemical reaction, maybe? You want to simulate that as just a source in our heat equation? Or electric resistive dissipation? That's another example, how you might simulate that mathematically. Or even nuclear fission. I mean, where you're not tracking the neutrons in the fissioning process. Somebody else has done that and given it to you, and there's a heat source. Where is it coming from? Something that you're not keeping track of necessarily in this heat equation. But it's some electrical, chemical, nuclear type of behavior. So let's break it down. Let's work on the net rate of increase of internal energy term, that accumulation. Oh, it can be negative, then it wouldn't be accumulation, it'd be depletion. The total internal energy would go down with time. The internal energy is the mass specific heat, put a P on that, specific heat constant pressure, times the temperature difference, the exact temperature at each location throughout the volume minus some reference temperature. Well, you sum it up by integrating over the entire volume. That's how you would get the total internal energy. Sum up over the little chunks of mass, over the little volumes that they occupy. So it's a volume integral. And we're interested in the accumulation, the rate of increase. How does it change with time? The amount that's stored. So it's the time derivative. That time derivative pushes inside the volume integral, and the mass density and the specific heat, to assume that to be constant, it attacks the temperature. The temperature, what's changing. So if it's increasing temperature, you're getting more accumulation. If temperature is going down with time, it's cooling off. There's a negative accumulation of internal energy. Now let's take a look at working on this conduction term, this net rate of heat transfer into the system by conduction. Well, first of all, look again at that control volume and identify what I show as blue little vectors, which are the outward directed unit normal vectors. Maybe the first time you're exposed to that when you did the differential and integral calculus class, which is a prereq to this class, you struggled with that concept. I assume that you have mastered that unit normal outward directed area vector. It shows the orientation. You multiply that by the small amount of the area, and now you're ready to do an accumulation. Well, then the local flux could be out of the control volume or into the control volume, the direction of Q double prime. It's given by Fourier's law as a reminder, the local heat flux at each point. You need to be able to evaluate that along the boundary of that control volume. So this is the net transfer out by conduction. When you have a dot product and two vectors, A and dotted with B, and they're in the same direction, what's the product? Positive. The magnitude of A times the magnitude of B. This is A and this is B. Just a little review of general vector dot product. If A was this way and B was that way, if you did the dot product, what would you get? It would be negative. It would be, the magnitude would be negative. And if the vector A was this way and the vector B was that way, you would get 0 because it's perpendicular. No flow across the boundary when it's just skimming along the boundary. That would be maybe, in this case, over here. True? No net flow in or out. But over here, what do we have? Net flow in. What about over here? Flow out. So you integrate over the entire area to get the net transfer out. And then I said, well, I'd really like the net transfer in. So what we do is we introduce the Fourier's law, the minus k grad t, and we get rid of that negative sign because we're saying we're now tracking in. So I switch a sign there. So the second term is the net rate of heat transfer by conduction in to the control volume, and it's given by an area integral. Let's go to the next slide. So now the last term was the heat source term. Well, assume that they give you this volumetric heat source term. The textbook doesn't put a subscript on this, but I like a subscript on it. They just put Q dot. But that means watts per cubic meter showing up from chemical, electrical, nuclear, other type of reactions or occurrences. So if we integrate over the volume, we get the total. This could be a function of location. That Q dot could be a function of location. Often, most of the time, it's constant. It's not a function of location. So let's go back and combine these terms. The accumulation was a volume integral. The net conduction was an area integral. And the net source, due to the volumetric heat source, is a volume integral. We'd like to combine them. So the area integral can be converted to a volume integral. The divergence of k grad t. So you're switching from an area to a volume integral. Sometimes they say Gauss's divergence theorem. Okay. So now we have everything in a volume integral. We can combine them such that this is the integrand. We say, you know what? That volume was arbitrary. I can make it small. I can move it around. I can make it so small it's around a point. When I collapse it to a point, it still has to be true. It has to equal 0. Hence, you conclude that the integrand must be 0 everywhere because you can move the little volume around everywhere. So, this is the heat equation as we want to know it. This is your accumulation. This is your conduction. This is your source term. Hopefully we understand every one. This is del dot. What is that? Divergence of K, a scalar conductivity, times the grad of the temperature. The gradient of the temperature. If that K is constant, it can come outside, and we get del dot grad T. What is the shorthand notation for del dot grad T, the divergence of the gradient? Del squared T, known as what operator? Laplacian. It's a Laplacian operator. But we often work in the Cartesian. So here's the description, a reminder of those coordinate systems. You have a point, it's out here, we're interested in temperature as a function of x, y, and z. What do? You move some distance out in the x, you move some distance out in the y, you move some distance out in the z, and then there you are at the location of the point. So if you're working in a cylindrical coordinate system, we start referencing back to the rectangular familiar coordinate system, but we think about temperature as a function of r, phi, and z. What is r? Perpendicular distance, the shortest distance from the z-axis to that point. What is phi? Drop down and project that point's location into the xy plane, and then from the positive x-axis to that line is phi. And z is that distance up from the xy plane to the point. Good review? And then spherical. Now, also I should point out, sometimes textbooks have T, R, theta, Z. Sometimes they use, instead of phi, they use zeta, a theta. I'm more familiar with theta. So you may see me slip on that one. How about for the cylindrical? Temperature is a function of R, but that's not the same R as in the cylindrical. It's from the origin out to the point. Then phi, it's a projection down. Guess what? This phi and that phi, same, doesn't it? But theta here is the angle from the z-axis down, positive z-axis down to the vector going directly to the point. Now, I learned maybe temperature is a function of rho, theta, phi. Doesn't matter. You just have to get whatever is the defined length scale and angles for the coordinate system, spherical coordinate system in the equations. How do you express it? But in this textbook, it's expressed with these terms in spherical and cylindrical. What do you need to express? The gradient operator. You need to be able to calculate and deal with heat fluxes. And in there, we need to do the gradient of T. Once you have the gradient of T, you multiply by K, minus sign, and you have the heat flux. So here it is in rectangular, pretty straightforward. Here it is in cylindrical. What's the challenging term? But which term do we often neglect, or we don't have? Temperature is not a function of phi often in most of the engineering problems. We may use the cylindrical coordinate system, but we may say, oh, the temperature is just a function of r, or the temperature is just a function of r and z. So often that term drops out. Excuse me. And then here it is for the spherical coordinate system. And you pick up the r, 1 over r d phi dr, etc. Okay? You take and you can go and get the divergence, combine it with the gradient. Hence, here is the full equation, heat diffusion equation. The source term is easy for all of them. The transient accumulation term is easy. But this is that del dot K grad T. That's expressed for the rectangular, for the cylindrical, and for the spherical. Again, often these terms are 0, and this is the surviving term. When you do one-dimensional heat transfer in a shell of a sphere, or in a sphere, just as a function of the radius. Likewise, this term is often 0, and that term is often 0, and this is the non-zero term in a cylindrical. Maybe I have a pipe and I wrap insulation around the pipe, and I'm interested in how the temperature changes through the insulation of a very long pipe. There you go. So now we need to talk about boundary conditions, because we have a PDE, we need appropriate boundary conditions. Let me introduce 4 types and discuss 4 types. Specified temperature, specified heat flux, insulated, which is the same as exploiting symmetry, and then convection boundary condition. Let's talk about it in context of a slab. And the slab has a center line and an x-axis. And the x-axis starts at the center line at x equal to 0 and goes to positive L at one surface, and it's negative L at the other surface. Okay. So what about a specified temperature at a boundary condition? That's pretty straightforward. You could say that the temperature at this point right here is given to be a constant value. Ts is 50 degrees C. Well, that's just saying that the temperature at x equal to L is a value known, Ts, constant. That's easy. Specified heat flux. Let's say on this side right here we have a heat flux that's coming in. What's it due to? Applied solar load, and we know that we multiply by the absorptivity, and that's how much is being absorbed into the solid at that surface. Maybe the light is shining on it, the solar load. Well, what we do is we do a quick energy balance, very thin control volume right at that surface. Energies coming in on the left. What's happening on the right side of the surface? It would be going out. So this is what's specified. The flux is specified. And how does it affect what's going out? Well, how does it transfer out on the right? How does it come out of that very thin control volume on the right? Conduction. It's the only way it can come out, conduction. So the heat flux, because we're working just on a unit area, for the conduction in the x must equal that. Well, what is it? It's minus k, the dt dx, and you have to evaluate it wherever that boundary is. Here I've shown it to be x equal to negative L. So one way to write an equation for the boundary condition for a specified heat flux would be, let me rewrite it right here, some given flux value specified times or equal to minus k dt dx evaluated at the x location of that boundary. Sometimes something's insulated. Let's say this was insulated right here. And this is the same coordinate system running out that way. Well, instead of applied heat flux, what is the heat flux if it's well insulated, perfectly insulated? It's 0. So you just say, oh, well, that's equal to 0. So for the insulated boundary condition, you get 0 is equal to minus k dt dx at x equal to whatever it is, negative L. Often we can exploit symmetry. So if this problem would have had a, I'm going to change it up again. Sorry about that. If this problem would have a specified temperature here, let me put it right here, of a value, and the same value specified temperature right there, and somehow there was a heat source in the material, the temperature you would expect profile to be maximum in the middle, and then symmetrical. You could cut it and flip it. So right here, the center line, if you had a constant heat source which didn't vary, it was uniform throughout, the center line is a symmetry line. Hence, you could write a boundary condition which would apply the rate of change of temperature with respect to x at x equal to 0 is equal to 0. There's no net flux across the symmetry line. That's another good boundary condition. And the last, the convective boundary condition, is the more difficult one. Let me try and draw it down here. We'll still have x equal to 0, and this is L, and x running that way. Let's say we had a fluid over here. And that fluid over here was at some temperature T infinity with some convection coefficient. So it could remove if T infinity is lower than the surface temperature, or it could add some heat if T infinity was greater. Well, let's draw it this way. We introduce a control volume, just like we did on the other side, a very small control volume, and we say the flux coming in on this side due to conduction only, not convection, it's just conduction only, equals what goes out on the other side by convection. And we combine Fourier's law, minus k dt dx, we evaluate it at the boundary x equal to L. Sometimes you'll put L minus with the little minus up there. You ever see a mathematician do that? Say, evaluate a little bit to the left of that location. But just, I think you understand, it's the derivative evaluated at L, x equal to L, and that's what comes in on the left, and it equals what goes out on the right, which is h times T surface, which is the temperature at x equal to L, minus T infinity. Thumbs up if that equation looks good to you. There's a nice little summary table in our textbook. Please spend some time looking at it, making sure that you can write these. So this is the most complicated when you have a convection boundary condition, because you have the temperature at the surface as well as the gradient of the temperature at the surface. Both come into the boundary condition. Ready to solve a problem? So we have a plane wall, it has thickness 2L, where 2L is 60 millimeters, so L is 30 millimeters, right? And X is going to extend from negative L to positive L. This is a pretty common way to set up the problem. So you have the center line, and you have positive L, and this is X. and this is negative L. Okay. Conductivity is 50 watts per meter degree C or degree K, it doesn't matter. There is heat generation in the wall, and its Q dot is given, so they give us K and they give us Q dot. Q dot's a whopping 5 times 10 to the 6th watts per meter cubed. The wall surface temperatures are maintained at 100 degrees C. So on both sides, you have what type of boundary condition is specified right here? Specified temperature. Temperatures on both sides are specified. All right, determine the steady temperature profile in the wall and express your answer in this form, where you're going to have T is equal to function A minus B x squared. If I said, kind of tell me what that looks like, you would say it's quadratic and it's concave downward, isn't it? And so it would be just like this, just like you might expect, quadratic and concave downward, symmetrical around x equal to 0. That's the temperature profile. So to solve for the steady temperature profile, we go back to our heat diffusion equation. We could go back and account for rho and C, rate of change of temperature with respect to time. Professor, you just said it's steady. I know, you're ahead of me. Put 0 there. Okay. And then it's one-dimensional in the x, so what we'll do is we'll put thermal conductivity, the second derivative of temperature with respect to x squared, plus Q dot. So basically, the equation boils down to this. 0 is equal to K, second derivative of temperature with respect to space, plus the heat source term. Good? So now we just say, that's my differential equation. I'm a good little mathematician right now. I need 2 boundary conditions because it's second order. One is very easy. The temperature, let's do this. dt dx at x equal to 0 is equal to 0. Symmetrical around the center line. And the other boundary condition, the temperature at L, x equal to L, is equal to the value Ts, which numerically is 100 degrees C. We'll leave it in symbols. So I go ahead and separate this equation. Let me set it up like this. I'm not going to go as slow and detailed for other problems, but if it's been a while that you did this, here you go. So I set it up like that, right? I rearrange the terms. And now I separate. What's the separation mean? I put the dx over here and I get rid of that. And then I integrate. And what we pick up is we pick up the derivative of temperature with respect to x is equal to minus Q dot x divided by K plus a constant of integration. I stop and I say, could I evaluate that constant of integration using the first boundary condition? Yes, you can. And so the first boundary condition says that the derivative when x is equal to 0 is equal to 0, and you conclude from boundary condition number 1 that the constant is what magnitude? We like that, don't we? Knock it out. But we already used that boundary condition, don't use it again. So now we separate and integrate. And then integrate T equal to minus Q dot x squared divided by 2K plus another constant of integration. Did I do that okay? Now I apply the second boundary condition number 2. This is boundary condition number 2. This was boundary condition number 1. And what we find is that Ts is equal to minus Q dot L squared divided by 2K plus C. I can now solve for C. Then I go back and stick it back into my equation. And what I find is that T is equal to Ts plus Q dot L squared divided by 2K 1 minus X over L squared. A little algebra, and you get it packaged up nicely. So if I said, what is my constant A in the equation, it would be Ts plus Q dot L squared divided by 2K. And if I said, what is my B, remember the B already has the negative in front of it right here in this equation. So the B is going to be a positive entity. It's going to be Q dot Q dot, you pull out the x squared, divided by 2K. Allow you to substitute some numbers and express your answer that way. But let's continue to part B. For part B, what is the maximum temperature in the wall? Where would be the maximum temperature? At the center line. Now, if you're like me when I first was taking heat transfer a long time ago, it's like, oh, I remember I have to take this arbitrary function, differentiate it, set it to 0, and then solve for the root, and blah, 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 and then test if it's a min, a max, blah, blah. Use some insight. It's at the center line. You can see that from the math as well, but go ahead and just say what would be the maximum temperature. Wouldn't it be Ts plus Q dot L squared divided by 2K? And then stick in the numbers, cancel your units, and you'll get something in degree C. All right. How about for part B, C? What is the heat flux at the wall surface? So what is the heat flux right here at that surface? This is Q double prime. Well, it's going to be a little different than at this surface. What's going to be different at the, it's going to be the negative sign because it's going out in the negative x direction. But if you look at the magnitudes, we know one is going to be negative and positive, but if we look at the magnitudes, wouldn't they be the same? In half of the heat that's generated due to some unspecified source is going to go out to the left and half to the right. So, how do I find what is that heat flux at the wall? You could do it one of two ways. Let's do it where you say, I'm going to apply Fourier's law, minus k dt dx, and evaluate that at x equal to L. True? You have your expression. When you calculate dt dx, you find that it's equal to minus q dot x divided by k. You evaluate that at L. So when L goes where that x was, and then you multiply by negative k, and that's the heat flux. You could probably see you can get rid of the negative signs, get rid of the k, and then you say, wow, that's a simple expression for the heat flux at the wall. Maybe I should put a subscript here, at L, at L, at L. It's just Q dot times L. Isn't that a pretty simple expression? There's a second way that you can get Q double prime. It's not going back to Fourier's law. How would you do it? Yes, sir.
Would that be the same for all symmetrical?
Well, I don't like the word all. I'd have to see a number of examples, but it's very common. Yeah. If you do this, let me answer your question a little bit later, but I asked the question, how can I calculate the flux at the wall a different way without using Fourier's law? Anybody want to suggest how to do that? Well, go back and just do a control volume and say, you know what? Everything that's generated on the right side of the half of it, the right half, is going out the right. How much is generated on the right side? Well, we have the volumetric heat generation multiplied by the volume, and it all has to go out the right side, which would be the flux at the wall surface times that area that it goes through. What's the volume? The volume would be the area times the length. And, oh, you see, look at that. The areas cancel, and we get the same result that we just had. So the balance, energy balance is conserved. I mean, that's great. Basically, the heat diffusion equation is the energy balance at each node or each location throughout the domain, at each point. All right. Now, a couple things to point out. Let me go to a new slide here. Is everybody done with looking at this one? Okay, insert new slide. If somebody would have said, here's the center line, K is uniform, Q dot's uniform, but I'm going to have a different value of the temperature, TS1 and TS2, and this is temperature, so which one's higher? TS2 is greater than TS1. Well, that changes it up. It's still going to have a quadratic profile, but the maximum is going to be shifted somewhere over here, isn't it? Maybe I didn't draw it that well, but it's going to be shifted away from that center line depending on how dramatically different those two temperatures are. And everything that's generated in this volume goes out that way. And everything that's generated from the peak goes that way. So there you have some non-symmetry. Okay. Okay, did anybody else have a question? We good? All right, let's go on. Let's say the problem is continued and they give you the density and the specific heat of the material. And they say the heat source is abruptly doubled. So you were running it and it went to steady state and everything's sitting there. But then all of a sudden it's doubled. The magnitude Q dot, the new heat source, is twice the original heat source. It's doubled. When that happens, what do you think is going to start happening to my solid slab? Don't lose your intuition. You probably had the maximum like this. When you double it, eventually it's going to go to a new steady state, which will have a greater maximum temperature, higher temperature profile, right? The surface temperatures don't change. Okay. So this node in the center line is going to start increasing in temperature. It's going to have a non-zero rate of change with time. So what they want you to calculate, what is the initial time rate of temperature change at the center line? What are they asking? Calculate dt d time at the location x equal to 0, right after it's doubled. We know that if you wait long enough, what's going to happen to dt d time at the center line? It's eventually going to go to 0. But right away, once you double it, there's the maximum. The temperature is going to start shooting up, but then it'll slow down and then finally get to the new value, and then you'll have a new steady state. True? So how do I solve for this rate of change of temperature with respect to time? Paint me a roadmap, right? Just tell me, start here. Go back to Fourier's law or go back to the heat diffusion equation? Go back to the heat diffusion equation. So let's go ahead and go back to the heat diffusion equation, and let's write it down twice. For the original case, what we had was 0 is equal to the rate of change of temperature with respect to time, with the K there, plus Q dot source for the original source. But now we have the new case, and the new case is rho C, rate of change of temperature with respect to time, equal to K, second derivative. I should put ordinary, change from ordinary to partial derivatives because now it's a function of space and time for the second case, plus Q dot new. Does that look okay? All right. Now what I do is I say, what is this new? We already talked about it being a doubling of the original. So I can just replace that by Q original plus Q dot original. And then I say, abruptly, right away, the initial time rate of change of temperature is immediately after it's the abrupt change in Q dot. Well, these summed to 0 at that beginning state. So this sums with that. Essentially, 100% of what the original heat source was being taken care of by the temperature profile, by the gradient. Now, because you've doubled it, that's the addition. And now that's going to result in a heating up. And so you say, I'm going to evaluate the rate of change of temperature with respect to time. I'm switching back to an ordinary derivative, and I'm only focusing on the location in the middle, the center line, is equal to the original divided by rho c. Where's k in my answer? It's not. What do I anticipate for the units on this? Just look, dt, d time. What do I want for SI units? Temperature change per time second, so degrees C per second. Let's take a look at putting in our magnitude of values, and just, I'm going to not run through the calculation, but what do we have? We have 5 times 10 to the 6 watts per meter cubed. That was our heat source. Our density is 1,200 kilograms per meter cubed, and our specific heat is 800 joules per kilogram Kelvin. Let's get rid of that Kelvin and put it degrees C. I can do that, right? You follow the logic on that? So we get rid of the kilograms. We know that a watt is a joule per second. And so we're just being very cautious and taking our time with unit conversions, meter cubed, meter cubed. And what do we get? We get the right units of degrees C per second. All right? All right. Next problem. I have a long, solid rod of radius Ri. Right here is the radius Ri. And it has conductivity K rod, or conductivity of the rod. In the illustration, they don't put ROD, they just K sub R. And it's subjected to uniform volumetric heating at a rate Q dot. So this is Q dot in that rod. What's it coming from? Electrical, nuclear, chemical, something. But it's showing up. The rod is wrapped in a cladding material of outer radius RO. So the cladding you see is different tinge of color in the illustration. But the cladding has no Q dot in it, does it? There's no heat source in the cladding. It's only in the interior of the rod. There's fluid overflow over the boundary, or the outer part of the cladding, at convection coefficient H and temperature T infinity. For steady state conditions, write the differential equation or equations and appropriate boundary conditions that could be used to solve for the temperature distribution in the rod and the temperature distribution in the cladding, but don't solve it. Just write the equations. So what would they look like? It's steady state, so we have no transient term, right? What type? I heard it already. Cylindrical coordinate systems. And is it one-dimensional cylindrical, or is it R, B, and Z? It's just one-dimensional, right? Just one-dimensional. So I'm going to put 0 for the transient part, and I'm going to write the differential equation for heat diffusion equation in the material known as the rod, and then I'm going to write the same heat equation, differential equation, for the cladding material. And both of them are operating at steady state. So we'll pick up the K 1 over R derivative with respect to R dt dr, and that is our Laplacian in the R cylindrical coordinate system. And then what we have over here, we have plus Q dot. And so this K is the thermal conductivity of the rod, I'll guess a single subscript. And that's the Q source in the conducting rod. Okay. How about in the cladding? We'll have K of the clad. We'll have 1 over R derivative with respect to R of R d T dr plus 0. There's no heat source. Somebody says, are you going to have an equation sheet for this class? Yes, we are. We're working on it. And what I did was I went back to this big equation right here, and I said, steady state, only in the rod, neglect, it's 1D in the radial, and I pulled that K outside, constant K. That's it. Okay. All right, now that I have 2 differential equations for each of them, I need appropriate boundary conditions. How many boundary conditions do you think I need? 2 for each. So for the whole works, I'm going to have 3 and 4 boundary conditions. True? All right, where do we want to start looking? Look from the inner going outer. So look at R equal to 0. Any boundary condition you can think of, R equal to 0? Symmetry, hence the flux has to be 0, or the temperature gradient is symmetrical. So we find here that the rate of change of temperature with respect to R at R equal to 0 is 0. That's boundary condition number 1. Any other? Let's go out to the RI, the interface between the rod and the cladding. Then there's no temperature discontinuity. It's going to have the same temperature right there, isn't it? So what you have to do is you're going to say, I'm going to solve for the temperature profile in the rod and the temperature profile in the cladding, and they have to match up. So the second boundary condition would be something like this. The temperature in the rod at R equal to R inner is equal to the temperature in the clad at R equal to R inner. That may seem obvious, but you need sometimes mathematical boundary conditions which are pretty obvious. I can't have a temperature as I approach from the rod and the temperature going to the same interface and they be different. But what else has to be consistent at that interface? Maybe I blow it up and think about it as a wall. I have the rod here, and then I have the clad here. I know there's some curvature here, but what's consistent? The flux, the heat flux. How can I draw the equation for the heat flux? Well, that'll give me my third boundary condition. And you say, let me get rid of that illustration to make some room. Negative K of the rod, the rate of change of temperature with respect to R at R equal to R inner, equal to minus K of the clad, the T dr at R inner. Does that look good? Good. The last one, what about out here at the outer radius, R naught, where we have convection? Well, you would say the conduction, you just the same thing. You have a little thin control volume, and you have conduction in the cladding and convection off the surface of the cladding. So boundary condition number 4 comes in at minus K sub C, the conductivity cladding. The rate of change of temperature with respect to R at R equal to R naught. I should have added that this is the rod, and that's the clad. And this is the clad, because that's the profile there. Okay, is equal to H T at the surface, which is at R naught, minus T infinity. Did that look good? We'll be done with this chapter. I told you it was highly mathematical, This is the type of thing that you want to take out of this chapter, and we'll move into more engineering in Chapter 3 next time. Have a safe holiday. We'll see you later.